This is the lecture for additive manufacturing, lecture number 8. And we are going to be continuing to talk about the powder-based forming processes or PBF process. So we will continue that. And so PBF is the powder bed fusion process. So SLS and other types of processes. So uh, most of the processes, all additive manufacturing processes are mostly line-wise and layer-wise processes. So PBF is also a line-wise and layer-wise process, but the main difference is that you are going to be using some expensive laser or electron beams, and most often these beams can only process one point of material at any given time. So the overall cost of the systems is very high. So unlike the extrusion based processes which have some really cheap machines on the market now, we still do not have any process less than maybe like $100,000. They are pretty expensive processes because you need lasers, and you need lasers that can melt materials or bond materials together. So because of that, the overall cost of the systems is always high. But there is always considerable room for improvement. So if any of you want to start a company that can produce um, even reasonably good laser-based processes that can cost less than $10,000, I think that is a great way to get an entry into the market. Of course, there are a lot of organizations are working on this, developing ways to fuse lines or layers of material at any given time. So these processes can be divided into three main processes. And uh, these processes, especially for the advanced materials type of processes, advanced components type of processes, infrared energy is used to induce the fusion in powder beds, and there are key differences in the control of which portions of the powder bed fuse and which remain unfused. So these are the three different types. One is the mask based sintering. The other one is you add an agent that can improve the absorptivity of the powder to the energy being delivered. And the third one is you add an inhibitor outside the part so that it will not join, but the remaining portions only will join. So mass-based processes is similar to the cubital process, which is one of the earliest 3D printing techniques that was developed for photopolymerization, and it is defunct now. And in this case, it needs to the powders need to be able to absorb the infrared energy. So the color choices of the part is limited. So it has to be either silvery finish or a slightly dark kind of a finish. The high-speed sintering process was developed at Loughborough University in England, and they had developed some inks specially formulated to improve the infrared absorption of the powders compared to the surrounding powder bed. And the infrared heater is used to scan the entire powder bed quickly following ink jetting. So this is again a process of an example of a line-wise process. So the main advantage with this technique, unlike the other traditional SLS and things like that, is that if you apply the energy on the entire powder bed and only some part of it will get bonded together, so you can increase the speed of making the parts tremendously. The the third kind is the selective inhibition sintering technique, where fusion is not desired and the inhibitor will interfere with the diffusion and surface properties to inhibit the sintering. So, and you can also have movable plates to mask portions of the powder bed where you do not need any or you do not want any sintering. So, what are the benefits of this process compared to the other methods? Um, it does not involve adding the infrared absorption agent into the part itself. The untreated powder becomes the material in the part, but unfortunately, the unused powder is not easily recyclable as it has been contaminated with an inhibitor. So there is um, quite a bit of unrecyclable material that is created by this process. So those are the pluses and minuses of this particular variation of the powder-based fusion process. So that that are the variations of the PBF process. Now, what are the process parameters for powder bed fusion? There are four different kinds. One is a laser related parameter, the other one is a scan related parameter, the third one is a powder related parameter, and the fourth one is the temperature related parameter, and the description of each of them is given under that. And each of these conditions and parameters are strongly interdependent and mutually interacting. So, one can affect the other. So, what are the laser related parameters? Main thing is the required laser power, which increases with melting point of the material and lowers the powder bed temperature. It varies depending upon the absorptivity characteristics of the powder bed. So depending upon the type of powder, this can change, and it is also influenced by the material type and powder shape, size, packing density of the material. So the closer the packing density, the higher the packing density, the higher the power required, and so on. So uh, the next one is the scanning mode, which is the next set of parameters. It can occur in two modes. One is the contour mode, which lays down the outline, and the second kind is the fill mode, which will go and fill in the inside of that contour. And the contour mode is done for accuracy and surface finish, so that the surface finish of the part is as good as possible. So the slower you make the contour mode, the better the surface finish. The fill mode is a little bit more complicated, and typically it is scanned using a rastering technique. So you put the powder and you scan using the rastering technique. But even in the rastering technique itself, you are not going to be putting the beam across the entire raster cross section. It is only incrementally moved over the width, and so there are two axes in this. So the one axis is moved across the laser scan width, and the other one is continuously swept back and forth across the part being formed. And in many cases, the fill section is subdivided into squares, and each of those squares is processed separately and randomly. And you do it randomly so that one part of the component doesn't get too hot and create preferential directions or residual stresses induced by the scanning. So you do that in a random manner, and it's entirely random manner controlled by the software. So this one gives you a brief introduction of how that scan strategy can be used. So you first lay down the contour, and you next divide this remaining region inside into squares, and you go and you might do this here first and then go and do this here, so that there is no preferential heating up and residual stresses being created in this part. And mainly this is for metal parts. So you can have a very simple raster part for polymers and other low temperature processing. But if you have metals, you got to make sure that you don't do it that way. Now, the, the powder shape, size and distribution can strongly influence the laser absorption characteristics and the powder bed density and the powder spreading. So if you have finer particles, it gives you greater surface area, but you remember this, finer metal particles are extremely pyrophoric. What does pyrophoric mean? Pyrophoric means it can catch fire. So you got to be extremely careful, and you are hitting it with a laser. So the inside of your envelope has to be in an inert atmosphere so that the powders do not catch fire, powders do not get oxidized and so on. Now, you can control the two, so they all must be balanced to provide the best trade-off between dimensional accuracy, surface finish, build rate and mechanical properties. The powder bed temperature should be kept uniform and constant to achieve repeatable results. So if you have high laser power and high bed temperature, it can produce dense parts. But what is the difficulty with that? What is the issue with that? Is that once the parts are formed, the grains can grow and the parts can grow. So, and the powders, whatever remaining powders are there, you can't recycle them very easily, and it is extremely difficult for you to clean the parts. So you may have to end up having to do final machining of the part. But if you use low laser power and low bed temperature, it produces better dimensional accuracy, but it will produce lower density parts and a higher tendency for layer delamination because those layers cannot bond well together. You need energy input to fuse the powder into a usable part, and it is a function of the laser power, the spot size and scan speed and bed temperature. And what you need to understand is that longer the laser sticks to a particular location, the deeper the fusion depth and larger the melt pool diameter. And typical layer thicknesses range from zero point 0.1 to 0.15 millimeters. So about 100 to 150 microns. As I said to you, the powder bed density and part quality is also controlled by the powder shape, size, distribution and spreading mechanism. So, I mean, you remember that we talked about the different kinds of spreading mechanisms and so on. So those things will control that. And typical powder bed densities are 50 to 60% for commercial powders and 30% for irregular ceramic powders. The melt pool formation characteristics are determined by the total amount of applied energy, and also they are also function of the absorbed energy density. And so let's look at what is the absorbed energy density. So you have a simplified energy density equation. A lot of people have used that and come up with different ways of correlating that to the input process parameters, to the density and strength of the produced parts. So this is an equation. It's a very generic and I would say uh, it's a kind of an approximate equation. So our understanding is that the applied energy density is a function of the laser power and inversely proportional to the scan velocity and the scan spacing between the parallel scan lines. So main thing that controls the energy density is the laser power. Now scan velocity and the scan spacing are not that big numbers, but the main thing is the laser power. So very straightforward, it is directly proportional to the laser power. Increasing laser power, it increases the applied energy, and it decreases with increasing velocity and scan spacing. And typical scan spacing values are about 100 microns, whereas typical laser spot sizes are approximately 300 microns. Now, this equation does not include the powder absorptivity, heat of fusion, laser spot size, or other important characteristics. But it is a very simplified analytical approach for optimizing the machine performance. So, for any given material, laser spot size and machine configuration, you can run a set of experiments to determine the minimum applied energy necessary to achieve good bonding between the different layers and the final material properties. So this equation is reasonably effective for powder bed fusion of polymer materials. Many times what happens is that if you have metal powders, there is a phenomenon called balling. What is balling? I mean, those metal powders can just ball together and form areas where you have um, some grouping of metal powders, whereas in the other area it is not there at all. And it is a function of the surface tension of the metal pool, the gravitation and additional forces. And if your surface tension forces goes above a combination of dynamic, fluid, gravitational and addition forces, then it can form a ball. And I realize this may not make sense to you, but it is important for metals, but not that important for polymers. The surface energy driving force for the metal powders to minimize their surface area to volume is much greater than the driving force for polymers. So that's why this is important for metals, but not that important for polymers. So here is an example of the different processing conditions and how that line width can control the balling up. So here you can see that there is a lot of balling up, and here also there is a lot of balling up. So this is for a specific type of metal powder. I believe it is stainless steel powder, and you can see that there is a definite correlation between laser power and the scan speed for bonding, and it will also show that depending upon the processing conditions you have different kinds of surface finishes. And this optimization is very complex for metals, and a simple maximization or optimization is really not that possible. So, but you can use this equation as a guide for process optimization, but you still have to run a few experiments before you can finalize the or hit upon the final parts. And sometimes you have to do this optimization every week or every month, every time you change your powders, every time you change the processing conditions, etc. You have to do that. Because what happens is that there are a lot of conditions that are different, like humidity on the shop floor is different, the temperature of the powder bed is different, the temperature of the envelope is different, and so on. So you may have to run this optimization, maybe a few layers, to make sure that the powders are bonding well together, powders are forming layers, and so on. So before that, you don't want to start your process and lose a lot of money. So what happens if you are going to have overlapping scans, and if you have multiple scans on the same area, those kinds of scanning and rastering patterns can make a huge difference in the final properties of your component, because they will create different multiple dynamics than single scan tracks. And if the laser returns to the spot again and again, it has similar effects to a longer dwell time or lower scan speed. So if you are going to have multiple pass scanning, you may want to do rapid scans so that you're not going to be dwelling on the same spot and increase the temperature and change the properties of your powders after the part is made. Many times, as I said earlier, you may want to change the whole cross section into small squares, and that can help to avoid the balling effect of these powders. And each of those squares is scanned individually while still utilizing high scan rates. If you are going to have the scanning over a longer length or longer track length, you are going to be increasing the residual stresses and part warpage. So if you are going to have metal powders, then those you may want, in the scanning pattern you might have smaller squares. So what are the materials used for the powder bed fusion process? Thermoplastics, polyamides, glass-filled polyamides, so that will have lower ductility than unfilled polyamide. You can have polystyrene, which has got low residual ash content, which is typically used for investment casting patterns. You may have polycarbonate and polystyrene that are amorphous. So when you make the part, it will end up becoming a very porous material. So you'll have to go back and fill it back up with another material so that you can remove all the porosity. You can also have elastomeric thermoplastic polymers, biocompatible materials like hydroxyapatite and calcium tricalcium phosphate. Um, 3D Systems and EOS have been making these metal powders for a very long time. So 3D Systems, it comes from DTM. DTM is the initial company that made the selective laser sintering process. So those powders are called rapid steel, and what happens is that when you make the rapid steel part, it has a lot of porosity, so you have to go back and fill it back up with copper. So the part that you are going to make, that you end up making, will have an orange color because of the copper. EOS made powders that are called laser form ST100. It is mainly a stainless steel type of material. There are also other proprietary metal powders like Ti64, cobalt, chromium, moly, numerous metal alloys, tool steels, etc. etc. So these are all made by powder bed fusion process and selective laser sintering or lens, etc. Okay. So what are the capabilities and limitations? Most of the time, thermoplastic powders do not require any kind of support structures. But in the case of metals, you need support structures, even though the powders themselves can act as supports. But since you're going to be introducing a lot of residual stresses, you want to make sure that the support structures will help to prevent the warpage in the case of metal parts. So the part that you are going to create needs to be removed from the bottom plate. So you are going to have some post processing which is expensive and time consuming. If you have small features like internal cooling channels, etc., you don't really need a support structure. So most of the time your part itself is constrained to substrate at the bottom of the build platform to prevent the warpage. So what can we say about the accuracy and surface finish of powder bed fusion process? Typically not as good compared to the photopolymerization type of process. And the accuracy and surface finish is strongly influenced by operating conditions and powder particle size. So if you have finer particle size, it produces smoother, more accurate parts, and larger particle size will provide easier powder processing and delivery, but it will hurt the surface finish, minimum feature size, and minimum layer thickness. So these things are all controlled by the machine. So you should be able to, your uh, process, optimization process should be able to help you to define what are the optimized conditions. Typically, powder bed fusion process can have up to 3 to 4% shrinkage. So there is going to be part distortion. So typically we would like to have materials with low thermal conductivity that will give you better accuracy as melt pool, and solidification is also much more controllable for these materials. If you can remove the heat as quickly as possible, then the part growth is minimized. And or if your part can have less thermal conductivity, then also the part growth is minimized. What can we say about the part construction time for powder bed fusion process? It can typically take much longer than other additive manufacturing processes because there is going to be preheat and cool down, etc. So these things are all going to be controlling the final component designs and parts. If you can have removable build platforms, then it can enable the preheat and cool down done outside the build envelope after the part is made. So that can improve the productivity of the machine. But many times you can also think about it this way. If your part won't have critical residual stresses and so on, then you might be able to nest the parts, especially polymers, in 3 dimensions, as you don't need any kind of support materials. So which means that you can make much more parts than a single one in a single run. So if your part requires supports, then this process can really be helpful to reduce that. So I would like to bring across homework number 6. So I would like you to do an internet search, find a set of recommended processing parameters for nylon polyamide, because that is the most common PBF material, using laser sintering. And if you can apply the applied energy density equation, I want you to tell me if these parameters are limited by machine laser power, scan spacing, or scan speed, and if yes or if not, why. Okay, so that's about it I have for lecture number 8, and I will be continuing with lecture number 9.